Hello everyone, welcome to today's session. In this session, we will learn about the support vector machine, which is also a supervised learning algorithm. So let's start the session. SVM or support vector machine is one of the most effective machine learning classifiers, and it has been used in various fields such as face recognition, cancer classification, and so on. Today's session is dedicated to how SVM works, the various features of SVM, and how it is used in the real world. Now let's move on and see what SVM algorithm is all about. So guys, SVM or support vector machine is a supervised learning algorithm which is mainly used to classify data into different classes. Now, unlike most algorithms, SVM makes use of a hyperplane which acts like a decision boundary between the various classes. In general, SVM can be used to generate multiple separating hyperplanes so that the data is divided into segments, and each of these segments will contain only one kind of data. It's mainly used for classification purpose where you want to classify or data into two different segments depending on the features of the data. Now, before moving any further, let's discuss a few features of SVM. Like I mentioned earlier, SVM is a supervised learning algorithm. This means that SVM trains on a set of labeled data. SVM studies the label training data and then classifies any new input data depending on what it learned in the training phase. A main advantage of support vector machine is that it can be used for both classification and regression problems. Now, even though SVM is mainly known for classification, the SVR, which is the support vector regressor, is used for regression problems. So SVM can be used both for classification and for regression. Now this is one of the reasons why a lot of people prefer SVM because it's a very good classifier and along with that it is also used for regression. Another feature is the SVM kernel functions. SVM can be used for classifying nonlinear data by using the kernel trick. The kernel trick basically means to transform your data into another dimension so that you can easily draw a hyperplane between the different classes of the data. Nonlinear data is basically data which cannot be separated with a straight line. So SVM can ever be used on nonlinear datasets. You just have to use a kernel function to do this. So guys, I hope you all are clear with the basic concepts of SVM. Now let's move on and look at how SVM works. So there's an order to understand how SVM works. Let's consider a small scenario. Now for a second, pretend that you own a fur and let's say that you have a problem and you want to set up a fence to protect your rabbits from the group of lions. But where do you build your firms? One way to get around the problem is to build a classifier based on the position of the rabbits and birds in your pasture. So, what I'm telling you is you can classify the group of rabbits as one group and draw a decision boundary between the rabbits and the world. So if I do that and if I try to draw a decision boundary between the rabbits and the lion, it looks something like this. Now you can clearly build a fence along this line. It simply terms this is exactly how SVM works. It draws a decision boundary which is a hyperplane between any two classes in order to separate them or classify them. Now I know you're thinking, how do you know where to draw a hyperplane? The basic principle behind SVM is to draw a hyperplane that best separates the two classes. In our case, the two classes of the rabbits and the lion. So you start off by drawing a random hyperplane and then you check the distance between the hyperplane and the closest data points from each class. These closest on your data points to the hyperplane are known as support vectors, and that's where the name comes from, support vector machine. So basically the hyperplane is drawn based on these support vectors. So guys, an optimal hyperplane will have a maximum distance from each of these support vectors. So basically the hyperplane which has the maximum distance from the support vectors is the most optimal hyperplane, and this distance between the hyperplane and the support vectors is known as the margin. So to sum it up, SVM is used to classify data by using a hyperplane such that the distance between the hyperplane and the support vectors is maximum. So generally your margin has to be maximum. That way you know that you're actually separating your classes between the two class is maximum. Now let's try to solve a problem. So let's say that I input a new data point. This is a new data point, and now I want to draw a hyperplane such that it best separates the two classes. So I start off by drawing a hyperplane like this, and then I check the distance between the hyperplane and the support vectors. So I'm trying to check if the margin is maximum for this hyperplane. But what if I draw a hyperplane which is like this? Now I'm going to check the support vectors over here. Then I'm going to check the distance from the support vectors, and for this hyperplane it's clear that the margin is more. When you compare the margin of the previous one to this hyperplane, it is more. So the reason why I'm choosing this hyperplane is because the distance between the support vectors and the hyperplane is maximum in this scenario. So guys, this is how you choose a hyperplane. You basically have to make sure that the hyperplane has a maximum margin. It has to best separate the two classes. So far, it was quite easy. Our data was linearly separable, which means that you could draw a straight line to separate the two classes. But what will you do? If the data set is like this, you possibly can't draw a hyperplane like is on it. It doesn't separate the two classes at all. So what do you do in such situations? Now earlier in the session, I mentioned how a kernel draw can be used to transform data into another dimension that has a clear dividing margin between the classes of data. So kernel function offer the user this option of transforming non-linear spaces into linear ones. Non-linear dataset is the one that you can't separate using a straight line. In order to deal with such datasets, you are going to transform them into linear datasets and then use SVM on them. A simple trick would be transform the two variables x and y into a new features space involving a new variable called z. So guys, so far we were plotting our data on two-dimensional space. We will only be using the x and the y axis. So we had only those two variables x and y. Now in order to deal with this kind of data, a simple trick would be to transform the two variables x and y into a new feature space involving a new variable called z. So we are basically visualizing the data on a three-dimensional space. Now, when you transform the 2D space into a 3D space, you can clearly see a dividing margin between the two classes of data. You can go ahead and separate the two classes by drawing the best hyperplane between them. That's exactly what we discussed in the previous slides. So guys, why don't you try this yourself? Try drawing a hyperplane which is the most optimal for these two classes. So guys, I hope you have a good understanding about nonlinear SVM. Now let's look at a real world use case if it supports vector machines. So guys, SVM as a classifier has been used in cancer classification since the early 2000s. So there was a experiment held by a group of professionals who applied SVM in a colon cancer tissues classification. So the dataset consisted of about 2000 transmembrane protein samples and only about 50 to 200 gene samples were input into the SVM classifier. Now, this sample, which was input into the SVM classifier, had both colon cancer tissue samples and normal colon tissue samples. Now, the main objective of this study was to classify gene samples based on whether they are cancerous or not. So, SVM was trained using the 50 to 200 samples in order to discriminate between non-tumor from tumor specimens. So, the performance of the SVM classifier was very accurate for even a small data set. We had only 50 to 200 samples, and even for the small data set, SVM was pretty accurate with these results. Not only that, its performance was compared to other classification algorithms like naive Bayes, and in each case SVM outperformed naive Bayes. So after this experiment, it was clear that SVM classified the data more effectively and it worked exceptionally well. Small data sets. So this was all about the support vector machine, which is a supervised learning algorithm. In the next session, we will learn about the unsupervised learning algorithm, K-means clustering. If you have any doubt, you can drop your doubts in the comment section. Thank you so much for watching.